Okay, so I'm going to give the talk for him. Yi-Hong Ang is the postdoc at the University of Pennsylvania, and he did most of the work. And the title is Validation of the Tissue Optic Properties Measurement using Diffuse Reflectance Spectroscopy. So we actually tried to use this so-called contact probe to determine the tissue optic property. And this experiment is done with so-called solid phantom with known optic properties, mu A, mu S prime. And of course, you all know that the tissue optic property, which include absorption coefficient and scattering coefficient, is important for photodynamic therapy. What inspired us to do this particular study is we have a phantom with known optic property. So on the very left is the expected optic property. And we use this contact probe, did measurement, which is shown here. We have another method that we believe more reliable, which is called transmittance spectroscopy. So the other method will give us some optic property mu A, mu S prime, which is sort of similar to expected value. But this contact probe, for example, give us values that's very, very different from what expected to be. So this is really a study to look into, is there a method to minimize this kind of large deviations of tissue optic property based on the contact probe, which has been commonly used in determining tissue optic property during PDT. So the objective here is to compare the accuracy of method to determine optic properties between the transmittance spectroscopy and the diffuse reflectance spectroscopy. And then we will evaluate an improved method, which is so-called the spectral fitting method, to see if the improved method will improve the results. Now, the method that was used in the previous example is so-called wavelength-wide fitting algorithm. And I'll explain what it is later. So this is the set of tissue phantom we're using. We have a 9 tissue solid tissue phantom with known optic properties. The mu A is combined from about 0.09 to about 0.45. Mu S prime is from 4 to about 16.9. So it's a full range which cover roughly the range of tissue optic properties. A little bit less than that, but it's pretty wide range. And the phantom is made of silicon, carbon as absorber, and titanium oxide as scatterer. The transmittance spectroscopy that we use is by introducing interstitial fibers into the phantom, and then we introduce a point source. Then we have another detector, which is isotropic detector. You can move it at different distance from the point source. So you will get a profile like that. And the profile actually is measured the absolute fluence rate as a function of distance from the point source, which is located at the center. And from this value, the fluence rate, absolute fluence rate per power of the source, which is known, one can actually determine the optic properties for these point source conditions. And for the contact probe, the way that we use is using an array of detectors and with single source. In this case, we're using this source 2 as our white light source. And then the detector at different distance in unit of millimeters. Sorry. This is from before. To determine the signal, and that signal is fitted to a known P3 approximation in a semi-infinite medium, and that allows us to determine the optic property. So here is actually a fit for a range of wavelengths from 621 all the way to 750, and you basically can determine this from based on wavelengths by wavelengths at about 6-7 different distance from the point source. And as a distance from 0.1 millimeter extending to about 0.9 millimeters. So the spectrum fitting that I mentioned is basically taking into account the known absorbent in the material, and then you can actually decompose the mu A by the different amount of material. So basically using the known spectrum behavior of material to constrain the fitting. So this is the method we use. We separate the absorption coefficient to a different components, and the mu S prime we're using me theory to constrain to this particular formula. A and B is fitting parameters. So here is the result of first part of fitting. On the very left is the range of phantoms with transmittance results. And in the middle is the wavelength-based fitting. And on the very right is spectral fitting for the same phantom. And you can see that the things that I marked in this red circle is showing that just wavelength-wise fitting will not give good results. Spectrum fitting clearly improves it, but it still does not solve the problem. They're still different from what it's supposed to be. So there is something that, in addition to just the fitting methodology, to improve the result, but it still is not getting the correct result in this particular case. And if you look at it from spectrum-wide result, this is the absorption coefficient as a function of spectrum plotted out. You will see that the dot is what it's expected to be, that we know at this point source we used some transmission spectroscopy, happened to be in that wavelength, so we measured it. And dashed line is the spectrum results, and the solid line is the wavelength by wavelength fitting. So you can see wavelength by wavelength fitting has introduced a lot of errors, which get smoothed out by using spectrum fit. So clearly spectrum fit will improve the result. But in this particular case, we find that they still will not be able to recover the correct results. We actually think that is due to the contact problems. So this is a remeasurement of the same phantom with more better contact between the contact probe and the phantom itself. And, sorry, this is wrong. What I said is this is actually percentage difference. So the worst case percentage difference is showing here. They can be up to 98% different for mu A, up to 97% different for mu S prime, and over 200% different for the RD. So the reason for this difference is really the contact itself. So we found that if there is a poor contact, you will get very poor results. You have to maintain the contact probe to have very good contact with the phantom itself. So here is one set of results that is making sure the contact is good contact for the same phantom. And same thing, this is interstitial results, wavelength-wide fit and spectral fit. And clearly the difference is much smaller. The percentage difference you can see here is drastically reduced from before. So these are percentage difference. And you can also see that the spectral fit will always improve over the wavelength fit. So in this particular case, we come to the conclusion that on average, using the contact probe, the mu A can have a mean uncertainty about 10%, and mu S prime has a mean uncertainty of about 17%. This is assuming everything is working properly, and if you use the spectrum fit to get the result that is more close to what is truly to be the result. So here is also for this good contact, what is the spectrum fit result? This is the dashed line, and the wavelength by wavelength fit, which is this kind of juggling solid lines. And you can see the spectrum fit clearly smooths out any of these uncertainties introduced by the wavelength by wavelength fitting. And this is mu A, this is mu S prime, this is the calculated reduced scattering coefficient, diffuse optic diffuse reflectance calculated. So we have applied this method in our clinic cases, which is in our plural photodynamic therapy. And we find that clearly in this set of measurement of different locations within the pleural cavities, wavelength-wise fitting is giving not as good a result as spectrum fitting in terms of extrapolating out optic properties. So this is actually what we're going to do in the future, to use spectrum fitting to reduce the uncertainty, in the wavelength range. And certainly that should improve the result, because we are now taking into account the wavelength dependence of the absorbance, which is not taken into account in this individual fit. And this is actually the components. Okay, so our solid phantom components showing here is mu s prime and the absorption for carbon. Okay, this is only one component here. And here is several components in our clinic cases, where you have deoxyhemoglobin, you have water, you have sensitizers in this case. So in conclusion, we have a very accuracy of optic property determination using diffuse spectrum spectroscopy implemented using a contact probe, and we find that a large error can cause due to fitting methods, as well as due to improper use. And wavelength-wise fitting can introduce large errors, and spectrum fit will improve the results. And we will have special thanks to Gerald Finley, who passed away recently, for developing these contact probes. And this is funded by a grant from NIH and PO1. Thank you very much.